Thanks a lot, and sorry for any delay to put my presentation on screen. And so, unfortunately, today my webcam is not working. I don't know what's going on, but I think that everyone already knows me. And I want to talk today about a kind of open book structure on the boundary of the real boundary of fiber for real singularities. It's when we were trying to prove such a kind of a result, of course we were inspired in some previous result by in the complex case, the complex sealing, by for instance for Ham or Helmut Ham, Nemeth Szilárd also, and also from Cobel, and but several other mathematicians somehow have been working in such a idea, such a structure on the boundary, like Sisma, Aguilar, Menegon, Aurélio Menegon, Bobadilla, François Michel, and Pichon, José Seade, and several many others. So I do not have a complete list here. But in the complex seedings, it's already known that when we start, for instance, it is stated in a very nice book published by Nemeth Szilárd concerning some studies concerning the boundary of the fiber. And he stated a result that was published was proved by Ham in 1971, more or less around that. It is published in German, so but it's a little bit hard for me to read that. Anyway, so but he stated the result from C3 to C2 in the ICES case, where if we start with ICES mapping from C3 to C2, where one of the coordinate function has a critical point at the origin, and when we consider the link of one of the coordinate function, so so on such a link, when we intersect with the variety of the ICES, we get a embedded of the link of the ICES in such a boundary, and then he proved that the complement of that it's fibers over S1, and in such a way we have an open book decomposition on such a link or such a boundary. And the link is such a case, since we are considering ICES and one of the function has a critical point of the origin, the link and the boundary of the minimum fiber, they are diffeomorphic to each other. So I'm unfortunately I'm not able to write it down the details here, but we inspired our result in a result like that. So let me start my presentation to show you somehow what would be what we consider as a kind of counterpart for the real case for such a result. And so let me start with some outline, and where I wanted to talk a little bit very quickly about some basic notations, definitions, introduce just to remember very quickly, remind very quickly the fibration, the complex case. Let me talk about some terminus condition, the composite of singularities, and by the end, and I hope everything will be well, and we'll be able to introduce a definition and then present our main results on such a concern. So basic notation, definition notations, of course. I hope everything is well. Can you see my screen very well in a very complete way, and also hear
Yes,
me?
Professor.
Okay,
Yes.
good.
Yes.
Nice. So so for me, F big F. Actually, I will change the notation here, and I will start with a. I will change the notation in the way I will start with a big F for a mapping, real analytic map germ, and in the middle of my presentation, I'll exchange the big F to small f because I wanted to use such a capital F for the mineral fiber. So anyway, big F is a real analytic map germ, and of course I wanted to work with some representative of that, and then but I will use the same notation for the germ mapping in the representative. I hope everything would be okay. No confusion will come up. And what else? So the zero locus, the variety or the zero locus of our map germ, I will denote by VF. And the singular locus is very well known. There's such a definitions. Is the point in some open neighborhood of the origin where our mapping does not have a maximal rank. And of course, I will consider all maps in set here as a germ in the origin. And so the discriminant set is the image of the singular set. And by definition, we say that F has a isolated critical value at the origin if the discriminant set is only the origin. It's equivalent to say that the singular locus of your mapping is included in the variety. So, as I said before, I will consider all maps in germ has a germ at the origin. And of course, analytic mapping here, analytic maps here, I will always be considering as a non-constant analytic map. So complex series, mean of vibration, just a quick review on that. And so given holomorphic function germ f, let's say f is small f from Cn plus 1 to C, prove that there exists a small enough radius, let's say epsilon is a positive real number, is small enough, such that the mapping phi given by f over the absolute value of f from the small sphere, or the sphere centered at the origin with a radius epsilon, minus when you remove the intersection of the zero locus with such a sphere, such a map provides you the projection of a locally trivial vibration from such a space to S1. It is very well known vibration called the mean of vibration or mean of vibration in the complex series. And what else? So I just have some few remarks on that. The space, the intersection of the zero locus with and the small sphere, it is called the link of the singularity, or the link of the singularity at the origin. And it's well known that such a space is well defined up to homeomorphism. But of course, if we consider zero has a isolated critical point at the for your function, it's well defined up to diffeomorphism. And the projection, it's also sometimes it's called the argument function, because it is related with the argument in the complex case. And we already know that if we assume that the zero is isolated critical point of your function, the fiber of such a vibration, it have the multiple type of bouquet of spheres, and the dimension of the sphere is exactly n. N is the middle dimension of the middle fiber, and the number of such spheres which appear in the bouquet. It's called the Mino number, and it's a very well-known number. It's a topological invariant of the singularity. So there are a lot of things that a lot of results and stuff that was developed around such a multiplicity, and but of course everything is known, or at least everything was developed in the complex setting, but in the real setting, this is a little bit complicated. I will move. So this is the idea concerning the immunovibration in the complex setting. So if we assume that 0 is isolated critical point at the origin, then we already have such a vibration, and we have a kind of the pair of the sphere and the link. It's provide open book decomposition of the sphere with such a projection, and that's the idea of the open book. So if you can see here, you see the image of a open book in the classical way, and that's exactly what's going on close to the link. Let me move to the next picture. So this is in the left side you find the a picture concerning the immunovibration. You see here the zero locus, like such a space in format in the shape of a V ladder, and the intersection between such a space and the sphere, it is here appears has a kind of cycle, a kind of one-dimensional sphere, and so in the complement of such a one-dimensional sphere here, on the sphere to S1, it is the immunovibration, but close to such a one-dimensional sphere, which is here is the link, represent the link, you have such a picture on the right side. So close to the link, the structure is like these ones. Is this the same idea of this picture here? Okay, so the bind is the link. The bind of the open book is the link. Is on the right side. It is represented here has k epsilon, and the leaves, which is the fiber of the open book, it goes to in such a neighborhood of in a some neighborhood of the link. It goes like this way. It's like a straight, like some planes. So exactly as we can see here in such a picture here. And of course, everything can be done in a very in a nice way, mathematically speaking, and that's what we want to recover somehow in the real case. And so in the real settings, what's going on? So can you hear? Are you still hear me?
Yes, we are here.
Just to have a feedback on that.
Okay.
All right, nice. So what's going on in the real case? So the real case, it is also possible to prove the existence of the immunovibration under some conditions, some interesting conditions. And but let me start with a definition. We say that a real analytic map germ, small f from Rm to Rn. I'm assuming here that m is greater than n at least 2. It admits a monotube vibration if there exists now 2 radius, let's say epsilon naught and eta, such that for each epsilon, so each positive epsilon less than or equal to epsilon naught, when we fix the closed ball B epsilon m bar. This is the closed ball on the source space, centered at the origin. The restriction, I mean, so we fix such a ball, and then we go to the target space, and we are able to, for such a eta radius, when we take the closed ball now in the target space centered at the origin, and with radius eta, and we punch such a ball, removing the origin. When we pull back that by our mapping F, such a restriction mapping here is a locally trivial, is a smooth locally trivial fibration. And such a, the diffeomorphism type of such a fibration does not depend on the choice of epsilon and eta, since it were choosing small enough. So that's the called the monotube fibration. In such a case, we also call the full monotube fibration. And that's the picture here. I don't know if you can see the idea of the picture here in the bottom part of the slide. Can you see that?
We see the picture.
Okay, good. And then, so how we can guarantee the existence of such a monotube fibration? So to do that, I needed to introduce more some field definition notation. One of them is they call it the monoset. So if we consider a real analytic map jet from Rm to Rn, and we can consider the singular locus of the pair f and the absolute of the square of the distance function, the origin. The singular locus of such a pair is what we call the monoset of our mapping germ F. And it is also called the polar set of F relative to the square of the distance function. And there are some few names concerned to this, like the points of non-transversality, the set of non-transversality between the spheres and the mapping F, and no regularity and things like that. But everything, the idea is just to consider the contact between the fibers of your mapping F and the sphere in such a case. The spheres centered in the origin. And so now let me introduce you very quickly the taming condition. We say that a real analytic map gem F from Rm to Rn is tame if we have such a condition here. Such a condition is a very geometric condition. It's a topological and also geometric condition, and but it is just somehow telling you that okay, when we fix a sphere of radius small enough, and we consider the link of our mapping gem F close enough to the link on the sphere, the fiber should cross such a sphere in a transversal way. That's the meaning of such a condition. And of course, it's a little bit weaker than the tone AF condition, in the sense that if your mapping F satisfies the tone AF condition, it implies such a taming condition, but the converse is not true. I mean, if satisfies such a condition, it not necessarily is a tone. It satisfies the tone condition, so it's a wider condition. So so such a, as far we know, such a condition was introduced in the first time. I mean, the sense related to the monofibration. in this paper published by David Massey, and it was in such a paper the name appear as the Milnor condition B at the origin. It's a very nice paper. And anyway, as I already mentioned before, the AF tone regularity along the singular fiber VF implies such a condition, but the converse is not true. And another interesting class of map game satisfying such a condition is the ICES map. Any ICES in this sense here, ICES for me is what sometimes is called the geometric ICES. It means that close enough to in a neighborhood of the origin, the singular set of your mapping will intersect the variety only at the origin. So anyway, this is just to show you that such a condition, taming condition, does not restrict only for isolated critical value. It can be considered in such a more general series here. So I don't know what happened, but it came up to here some message here, but I hope everything is still okay. Are you still there? Can you still hear me?
We are here, Professor.
Okay, good. Okay, let's move on. And so monotube vibration, just also introduce very quickly that. So if we start with reanalytic map jam from Rm to Rn, I will always consider m greater than n and at least 2 with isolated critical value and tame. Then Massey proves that it's possible to guarantee the existence of the monotube vibration on that series I showed you. And so since we have such a vibration in the inside the closed ball, when we consider the fiber of such a vibration, which is called the monofiber as well, the intersection of such a fiber and the boundary of the closed ball or the sphere, it is called the monoboundary, and that's the monoboundary that I will be working in such a result. So I just want to understand what's going on in such a, how we can somehow work a little bit on that. And of course, if you have a real mapping with isolated critical point at the origin, we know that such a condition is very strong. But in such a case, of course, we already have such a taming condition, because this is very well known that under such a very strong hypothesis of isolated critical point at the origin, the tone AF condition already holds. So this is just a remark, because Milnor, in his famous paper, famous book, he worked on such a case, in such a series. Reanalytic map jam, actually polynomial mapping with isolated critical point at the origin. So, but we have here such a condition, and Massey proved that in a more wider way. So let me move a little bit. Let me see. Maybe I don't know what's going on. Okay. It's okay. So from I don't know what. Okay, let me come. Okay, I got it. From such a monotube vibration, we can also consider such a vibration here. This is just a restriction. Instead of pull back the punch at the close the ball from the target space, we can just pull back the sphere or the boundary of the ball, and we have such a vibration here, which sometimes we call the tuber monofibration. It was also proved by Massa, and this is the idea of the picture in such a case. All right, composition of singularities. Let's move a little bit for a different topic, but everything is related in my case. So now I will change the notation here. Of course, I already. Unfortunately, I was not able to get a very a good uniform notation, but I'll change the notation here somehow. So, but small f and small g now is the mapping. Small letter will be our mapping. In the capital letter, I will just use for the monofiber related to for such a mappings. So, now we have a, let's consider a composition of a map germ F and G. Let's call that H. And we may ask some question. For instance, in the case that the discriminant F has a isolated critical point, have a isolated critical value, and G, what's going on with H? In such a case, it's very easy to show that it's just a very easy application of the chain rule that if both F and G both have isolated critical value at the origin, then H also have isolated critical value at the origin. So, but what if we consider F and G both tame? So the answer is no, it's not true that the composition of tame is tame. I invited you all to take a look in such a paper, which is published in the archive, but it was already accepted in a journal, and I hope we hope that it will be published very soon. And so in such a paper we discuss several questions related to these, the compositions and the tameness conditions, and also we were able to prove a characterization for that, and our characterization was like this. So if we consider F and G as before, and H the composition, H is the composition mapping, and if we assume that F is tame and also have isolated critical value at the origin, and G we just consider with the isolated critical value at the origin, or it can be a projection. It can be a discriminant empty, means G is a germ of subimmersion, which of course we can consider that it is a projection. So in such case, the composition is tame if and only if such a interesting condition here called the equation 4 holds. It's a kind of a tameness condition, but involving as well the composition of, involving the main function f, g, and h. So if you look here in the left side of such a 4 equation, you see the image by f of the monoset of 8 minus the singular set of 8, and take such an image, take the topological closure. So now you are in the target space of F, which is the source space of G, and when we intersect with the singular locus of G, if such intersection is only the origin, under our hypothesis, it's equivalent to guarantee that, to say that H is tame. So this is an interesting condition because, of course, now we can consider F and G both with isolated critical value at the origin and tame, and in such a way that such a condition holds, and then the composition is also tame. So since F and G both have isolated critical value at the origin, then H also has isolated critical value. So we have tube vibration for F, G, and H. And the question is, okay, how we can relate the topology of the mineral fiber of these three things, these three data. So that's the question. And one of the way we can study that is related the mineral boundary of these three things, the mineral boundary, the mineral fibers, and so on. So there are a lot of questions surround that, and I will be talking. I will talk about a little bit about some results that was recently published in this paper right here, and it's a paper authored by myself, by Menegon, by Ribeiro, by Sead, by Guarin, and I don't know if the time you permit me, but if okay, maybe I can also mention very quickly a result also published in a different paper by myself and Osamu Saeki, and also related to the topology of the mineral boundary for the composition. But maybe it's too much for today. But okay, let me move a little bit. So what's the first result I want to mention here is, so if you consider F a Taylor map germ with discriminant 0 or isolated critical value at the origin, and we may consider the projection on the target space. I'll call here by Y, the projection from Rk to Ry, and for each I which is less than K and at least 1. So I'm just considering projection. Doesn't matter the level you are. The point we proved that the boundary, I mean, the boundary of the mineral fiber. So on each case, we are able to prove that it is all same. But if you apply our characterization, it's very easy because the projection is submersion. So the singular locus is empty. So our condition is trivially satisfied. So it's same, and the composition means same, and also we have isolated critical value at the origin because this is the very well known that such a case, if we have isolated critical, if F has a isolated critical value at the origin, then the projection also has such a condition. Of course, it may be submersion as well, but the interesting case is when such a composition also have isolated critical value. But anyway, in such a case, the mineral boundary of the projection, the fibers of the projection that I denoting here about the boundary partial of capital Fy is obtained by gluing two copies of the mineral fiber when we consider the previous projection. Okay, let me explain that. So we are considering the projection from Rk to Ry. But before we go to Ry, we may project to Ry plus 1, and then from Y plus 1 to Ri. Okay, so that's what I'm talking about here. So when we consider the projection from Rk to Ry plus 1, we have such a stuff there with the mineral tube, mineral fiber, the boundary of the mineral fiber. Just consider the mineral fiber there, and then project again from Ri plus 1 to Ri. And then again, we have all this stuff. And what I'm saying here is that the boundary of the mineral fiber from Rk to Ri after the composition, it can be recovered from the monofiber, the gluing along the boundary of the monofiber, when you consider the composition from Rk to Ry plus 1. So I hope everything is clear. So I can try to draw a picture here if possible. But so that was one of our first result. But this open for a more general questions and results where such a generalized open book structures come in the picture. Okay, let me just give you a very quick definition and notations on that. I'm getting some delay here. I don't know if it's the same for you. I hope not. But now I'm following definition in the given by Hanik, Loyenga, and also for Winkelbeller. And so given M a closed smooth manifold, and N a submanifold of M of codimension K, the K at least 2, sorry, codimension at least 2. So the definition is, suppose that for some trivialization T of the tubular neighborhood of N on M, we have such a diagram here. So you see that in the picture, you consider the tubular neighborhood of N on M, and we remove a copy of N. And such a trivialization send you such a guy to N times the BK minus the origin. So N here is the copy, or the central copy of the copy, like the N times 0, which is say sometimes the central manifold. Okay, in such a tube. And then pi here in the vertical mapping on the left and the right side, such a pi here, we can consider that as is written here in the bottom part. So I don't know if you can see that here, pi xy is y over absolute value of I. So how we can see such a pi? We just consider the projection, projection in the second coordinate, okay, and then we modularize that to get such a pi here. So such a composition of T composed with pi on the 0 here in the diagonal, it is a trivial fibration. Okay, so and the idea is, okay, if it's possible to extend such a fibration on a fibration now from M minus N to the sphere, but of course it may not be extended in a trivial way. It will extend only as a smooth locally trivial fibration. If possible to do that, okay, we say that we have a generalized open book structure. Okay, I hope and so I hope the definition is clear here. And this is exactly what we get. And when we consider, for instance, a holomorph function from Cn to C, a holomorph function germ with a critical point at the origin. We have such a condition, not only the complex case, but also in the real case. I mean, for a real mapping from that's what somehow did in his book, for a real analytic map from Rn to Rm, or Rmm has in Mary, for Rn has in Navy, with a critical point at the origin. That's what we get that was called the what was called the minofibration. So this we have exactly such a condition. So it is a generalized open book. But the point is that we don't need to ask a critical point at the origin. We can do that in a more general way, and somehow, of course. And I don't know if can you see my slide? Okay. So this is has what I said. The pair MN is scalar generalized open books decomposition M with bind N, and the page is the fiber of such a fibration. Okay. All right. Let's move a little bit. Should go a little bit quick now. So now consider such a diagram here. Okay, we start with a Lali map germ from Rm to Rk, and we can do a kind of splitting of our mapping in two parts. So we can project from Rk to Ri, and also take the complement of that. So the second projection is from Rk to Rk minus y. So we are splitting our mapping, our previous mapping, in two pieces. Okay, and of course, if we consider that F is tame, and since we are considering projection here, so tame and with a critical value means that both compositions are tame and also have a critical value at the origin. So we have fibration, minofibration, tube minofibration on both sides. Okay, and then our main result here was, okay, in such a case, using such idea of the diagram, S here, small s, means the square of the distance function to the origin. So we were able to prove that if we consider F a tame map germ with a isolated critical value at the origin, and let's call small s is the square of the distance function to the origin, for each y such that k minus y is at least 2, and the singular locus of such a pair here, fk minus y over the absolute value of such a mapping, and S. So this is the monoset of such a projection here. We are asking that the monoset of such a projection is empty. Then the pair, the boundary of the monofiber of Fy, just keep in mind that we are working here with two different mappings. So we start with a central mapping from Rn to Rk, split that in two pieces, projecting that into Ry and also to Rk minus y, the complement of that. And then we consider the monoboundary from the mapping from Rm to Ri, and the monoboundary is just this notation, the partial of capital Fy, and we may consider also the monoboundary of the main map, the central map F. So what we are saying here is that this pair is a generalized Offenbook structure, and in such a case we are able to prove that the projection is exactly given by such a guy here, F subscript k minus y over the absolute value of this guy, okay, from the boundary of the Fy minus the boundary of capital F, small f, to the sphere Sk minus y minus 1. This is the main result of I want to talk today. Just show the main idea here. If I have time, how's about my time? How much time I do have?
Something about 5 minutes left.
5 minutes left. Okay.
A little bit more.
Yeah, sure. Yeah, maybe I will just give it so the broadly idea concerning the proof of such a result. Of course, the details, everyone can see, and I'm open to discuss that anytime in the published paper. And so just to give a ugly idea concerning the proof here, so we just started considering such a diagram here. What such a diagram says? So we under our condition, as I already mentioned, we have the monotube vibration for Fy, the projection on one side of such a diagram. Let's come back here very quickly. So again, we are considering such a diagram here. So we have a central mapping here from Rm to Rk, and then we can project to Ry and consider such a composition here, small f indexed with a bigger y on the left side, and also the small f indexed with the capital K minus y on the right side. So we have two mappings, and under our condition, both maps, they have the monotube vibration, okay? And we are considering the mono fiber for the mapping the left side and take the boundary. That's the notation of the partial capital F y. Okay, but of course we now may consider the mapping on the right side restricted to such a boundary. And so under our condition, we are able to prove that when we pull back the closed disk, the punched closed disk from Rk minus y for a small enough radius by f k minus y, intersect that with the boundary, we have in the horizontal mapping here, we will get a trivial vibration. It is not hard to show that. So you can see the detail in our paper, published paper, and then we can take such a vertical projection here, which is also trivial vibration, and then we have the diagonal mapping here from such a space to the sphere sk minus y, k minus y minus 1, we have a trivial vibration here. But we can also consider, as I will explain the next slide, but don't forget about this equation here, 19, 20, 21. It was just a mistake. So, but anyway, we can also, if you come back to the horizontal vibration, instead of pull backing the punch at the ball, we can just pull back the boundary. We still have a trivial vibration because it's a restriction of a trivial vibration. And then do the same on the vertical projection here, and we get also a vibration with the same mapping here on the boundary now. So what's going on there is just that kind of T vibration in a tubular neighborhood of the boundary of the capital F small f, that f, the main f, inside the boundary of the f of big F and big Y. So this is what's going on here. I can show you a picture later. And under our condition that I should, so G here is the don't forget that G is the square of the distance from to the origin. So this thing is set here is just the minus set of the such a projection. So since we are asking this is empty, we are able to prove that now this 20 equation here, 20 mapping here, this is also a vibration. And when we restrict such a vibration to the boundary, we get the vibration 19, which is in the top. And then if we glue everything together, we will get the vibration as I showed, as is shown here in a 21. This is a locally trivial vibration. And work a little bit, you can also prove that it's not, of course, as I told you, the details in everything is the paper, but we are open to discuss that in time. And we can show that the leaves of such a fiber, they exactly the mean of fiber of that main mapping. Okay, so this is a ugly picture. This like oval here represents the boundary of Fy, capital Fy, and this gray part here is that the pullback by Fk minus Y of the punched closed ball. Okay, and so these arrows here is just to show you what's going on in such a situation. So this line here, this cycle here in the vertical way, it's kind of punched cycle here. It is the fiber, the muon of fiber of that central mapping. Okay, and inside such a green part, it comes as a product between the boundary of such a muon of fiber times such a semi-interval here. And so this picture is also explained in our paper, and I hope have all of course I'm not giving you all the details, but it's just the some main idea what's going on in such a case. And yeah, thanks a lot. Muito obrigado.